We are back again, ready to improve our car and fix some very annoying problems. This time, we will give the car Shapecast wheels so it can go smoothly over bumps, fix sliding ramps and lateral collisions, and many more improvements. But before we start, let's do something that we should have done a long time ago, changing the physics engine. Starting from Godot 4.6, Jolt Physics is now going to be the default physics engine, so there is no reason not to use it anymore. So if you are on Godot 4.5 or higher, go to Project Settings, and under Physics 3D, change the physics engine to Jolt. And after a quick restart, we should now be getting a much more precise and faster physics calculation, just like that. Then we'll open the wheel script and rename a few variables. Here, I'll be changing the velocity variable to speed when it's a non-vector value. So we have the car forward speed at the top and the wheel forward speed used at the bottom. Now things should be hopefully less confusing. And another important thing before we start. The direction indicator we are using from global bases are not normalized. So if your Raycast node or any of its parents are scaled, you'll be getting completely wrong values for all your calculations. If you want to make sure to get correct values, you can add the normalized at the end, on lines that use the global bases vector. But I'll leave that to you. And just one last thing, if you remember previously, we had to disable the Raycast node and manually call force Raycast in the code to prevent the precision error caused by delayed checks. But while this works, we lose the debug shapes in-game, so I figured a proper way to make it work. First, select all the Raycast and enable them back. And to make sure we get the correct results, open the Process tab and set the physics priority to -1. This will make the nodes execute last and fix the precision problems without the manual Raycast. But now, let's really start. The first outstanding problem with the car is ramps. The car simply won't stay still on them. You can hold the brake all you want and it will still slide down. Not good. Even if we set the traction to 1 and hold the brake, it still slides. Something is definitely wrong here. So let's reset this value and get to work. Open up the wheel script, and in the spring calculation, we are going to take this spring force and save it into a variable named suspension force before you apply the collision normal. And down at the very bottom, after all the forces are done being calculated, we are going to apply a counter spring force to nullify some of the spring forces in the x and y directions, but only when the car is at a very low speed. So let's check if the wheel speed is low enough with ABS float, F speed, and choose a small value. You can adjust this value or turn it into a variable later. Then we are going to get the suspension force in the car y-axis, and then reduce the final z-force dot z-force based on how aligned it is with the global y vector3.up. Copy this line and do the same for the x-force dot x-next. And by countering the spring forces this way, we can make the car stop at low inclines, but it still very slowly slides down. So we are going to add another check just before the z-force calculation. Now we are going to set the friction to a very high value if the car is moving at a low speed. This can be a very low value, and it will work kind of like a static friction for our simulated wheels. But now our car perfectly stopped on ramps. And you can set the friction check speed to a very low value, just to stop that extra momentum. And it still works the same, successfully stopping the car. And of course, it won't work on bigger ramps, because we still have to fight gravity, and our counterforce is based on how aligned the car is with the up direction. Now with the ramp problems fixed, let's start turning the wheels into shapecasts. If you remember previously, one of the big hurdles of Raycast cars are small gaps. This is due to Raycast being a single ray and failing to detect gaps. So to fix this, we'll turn our wheels into shapes and sweep an area for collisions. Instead of replacing the Raycast wheels, we will be adding the Shapecast as an alternative, so we can turn it on and off depending on the type we want to use. So let's select our first wheel and create a Shapecast 3D node. Just make sure it is not the first child, because the script uses that for the mesh. Next, create a cylinder shape, or if you don't care for precision that much, using a sphere will give you much better results while being faster to calculate. But we'll use a cylinder here. Set the height to 0.2, how thick the tire is, and let me change the debug color to red, so we can better see what we are working with. Now, as you might have noticed, the cylinder is facing the wrong way, and it will sweep the shape in this direction. So let's set the target to 0 for now, and rotate the Shapecast in the z-axis by 90 degrees to turn it in the correct way, and set the radius to 0.33. Now, it's important that the Shapecast is at its origin, or a lot of things will break. If you need to adjust the Shapecast position, make sure you are doing so by moving the Raycast node above. So let's reset the position for the Shapecast node. And not forget to set the physics priority to -1, so we don't get precision errors. But because we rotated the Shapecast, now the target position Y is sideways. So we will have to remember, we need to adjust our X position instead. Make sure that -X goes down, which might be flipped in case you rotated the wheels the other way around. And for better performance, you can adjust the max results to 3, or some low number. And I will increase the radius to 0.35, just so we can see the shape debug over the wheels. Now copy the Shapecast node, and paste it inside all the other car wheels. They should all be already in the correct position. Which means it's time to start coding. First, let's create an export variable for the Shapecast node. I'll put it at the top. And now we need to assign each Shapecast to its wheel. Next, inside the ready function, we are going to check if we have a Shapecast. If we do, we need to adjust its target position, much like our Raycast node above. But we are changing the X here, because we rotated the node. And the Shapecast doesn't need the wheel radius anymore, because the shape itself has it. And finally, we need to call shapecast.addException, and give it the parent node, the car's rigid body, so it doesn't detect collisions with the car body. Then, in the wheel physics, we'll modify the pass condition. If you are not using the Shapecast, and the Raycast is not colliding, we don't calculate. And if you are using the Shapecast, and the Shapecast is not colliding, we don't calculate forces. Then for the contact point, if the Shapecast exists, we set the contact point to be the shapecast.getCollision.0. There can be more than one collision point at once, but usually getting the first one already gives us a very good result. If you want to calculate the forces for all the collision points, you need to create a loop and get the sum of the spring forces for all points, and not forget to divide the final suspension force by the total number of collision points. But we won't do that. Then, right at the end of the suspension force calculation, if we are using Shapecasts, we need to use shapecast.getCollisionNormal. And just like that, the car will now gracefully go over bumps, and behave much more naturally. And let's not forget to set the Shapecast target at the start of the physics, so we can change the spring length at runtime if need to. But we are not done yet. There are a few hidden problems with this yet. First, cylinders are not great. Besides being expensive to calculate, the collision point that is hit in the ground is a bit imprecise. If you take a look at this other car that has bigger tires, we can see why. The collision point in the ground is alternating between the left and right. This usually won't cause much problems, but just know that this can happen. Another problem is that the collision point we are getting, the green sphere, is not at the bottom of the wheel. So when we calculate the distance from the rest position to get the spring length like we were doing with the Raycast before, we might get slightly wrong values. We can fix this by calculating the red point instead with a bit of extra math, but the difference is usually not significant enough to notice, so we will leave it as it is. Now the other problem is this: we can get our wheel stuck inside the ground fairly easily. In this situation, the Shapecast is not detecting any collisions anymore, so no forces are being applied there. But if we move a bit, it might just be enough for it to work again. Not great. And it is fairly easy to get this problem. Any high enough jump will get you stuck with this. So why is that? Well, Shapecasts won't properly detect things already inside them, only objects that are hit after they have moved. If you take a look at the car and push it down, you can see the tire shape is pushed down at its most extended position. Although this gives us the correct collision point, there are situations that things just break and stop detecting at all. So to fix this, we are going to create a new variable called ShapeCastOffset of 0.3. We are going to use this to push our Shapecast above its rest position without altering the calculations. We just need to subtract the offset inside the target position calculation and set the Shapecast position.y to be the offset. This will push the Shapecast to be above its normal position, meaning it will be harder for the Shapecast to fail due to starting inside objects. You can play around with this value to find what works best for each car. But now, if we push the car down again, we can see the Shapecast stays correctly in place above the ground. And indeed, now we have working Shapecast wheels, and our little Jeep doesn't get stuck anymore. But before we finish, there is still another big problem with our code. Let's drive this car and take a closer look at the wheel's grip curve values. So far, everything seems normal. We have a variable grip similar to the real cars. But when we come to a slow lateral slip, we see a problem. Our car doesn't seem to want to stop, and our X traction graph is maxed out, giving us zero traction. Until we move again, and it suddenly goes back to normal. And it's even worse if the car is hit from the sides. It just starts moving without any resistance. Well, while cornering forces are simulating real forces, we don't simulate any real alternation the wheels might have. So when the car is moving sideways, we have a very high slip angle and get very little forces back, depending on the grip curve. To fix that, we are going to do something very similar to the ramp solution. So right after the grip factor is calculated, we are going to check if the car forward speed is low enough. And if it is, we force the grip factor to 0, meaning there will be a lot of force, and stop the car from moving. And just like that, now our car behaves more normally. We can take hits from the side, and sliding to a slow stop will now properly stop the car. But before we finish the video, let's make some minor improvements and changes to the code. First, inside the car script, let's update the get point velocity formula to take into account the center of mass of the car. Change the global position here to 2 global center of mass. Now our point velocity should be correct even when we are using a custom center of mass. Next, let's add a new property for the wheel called max spring force. This can be helpful if the car we have has long suspensions to better customize the behavior we want. Then inside the suspension force, we just need to clamp this value between our max spring force. So now by customizing this value, we can avoid our car jumping around if the springs are suddenly compressed. This is a bigger problem for Raycast cars, since they can have the spring get from 0 to max compression in an instant, but it is still a good setting to have. And finally, another problem for high suspension cars. When our Jeep goes over the ball, the wheel reacts like it should, avoiding the ball. But the rigid body ball is none the wiser, and stays in place. If you want to fix that, you can go to the very bottom of the wheel code and loop over the Shapecast collision points. If the collided object is a rigid body 3D, just apply a reaction force. Here I am just using the negative sum forces of the wheel. But you can fine-tune that later. Now the Jeep can go over objects and fling them around. And finally, we have a code we can remove. When using Raycast, we interpolated the wheel's position to give us better results, but Shapecasts usually don't have this problem. So you can increase the value or remove this entirely. But that's really it. We have a Shapecast car now, along with tons of other improvements and fixes to make it finally more stable. As always, if you would like to support me, you can get the project source files and experiments by supporting me on Patreon. Now you can go and customize your car to your own needs. I hope you like this video, and until next time.